Day 97 notes, pre-calculus. Let's start off today by doing some warm-up exercises, and we'll practice first by solving for x in the following equations. We have 10 equals 2x plus 6, so you should recognize that we'll subtract 6 from both sides. 4 would equal 2x, then we could divide both sides of the equation by 2 and find that x itself is equal to 2. Now we know that this would be a solution for a problem like this because when I put 2 back in place of x, I now have 2 times 2 plus 6, and that should equal 10. 2 times 2 is 4, plus 6 is equal to 10, so we know we have the proper solution. Let's work on a couple others. I have 60 equals 2x divided by 10. Well, my goal is to get x by itself, so let's multiply by 10 first on both sides of the equation. That leaves me with 600 equals 2x. From here we can divide both sides by 2, and this leaves us with a result, x is equal to 300. Again, we could check our work by placing 300 in place of x. 2 times 300 divided by 10 should equal 60. And 2 times 300 is 600. 600 divided by 10 equals 60. 60 equals 60. So we know we've done everything correctly there as well. Now this next question looks to be a bit more tricky at first, but truthfully it's not too hard to solve. We're again trying to get x by itself, and in order to do that we have to eliminate this square root symbol. Now you should recognize that in order to remove a square root symbol, all I have to do is square both sides of the equation. And in this case, x has to be 25. And that too should make sense because the square root of 25 is equal to 5. Notice here in this problem, we started with a positive square root. The symbol was already provided to us, so I didn't have to concern myself with a positive and negative answer. In fact, if you had placed a positive and negative answer in this result, you would have been incorrect, because the square root of negative 25 does not equal 5 at all. Square root of negative 25 would be 5i and negative 5i. Let's consider this next example. 3 raised to the x power is equal to 27. This is an example of the exponential functions we worked on last week. 3 to the x power is equal to 27. Now, right now, we don't have a technique that eliminates this 3 from the x. We don't have a technique that gets x by itself right now. So the best we could hope to do is guess and check here. And fortunately, we would be okay. We can find the solution. If we can think of a number that 3 would be raised to in order to equal 27, then that number would be our solution. And I know that 3 times 3 is equal to 9, and 3 times 3 times 3 is equal to 27. Because I multiplied 3 times in a row, then that would be my power. 3 to the third power is equal to 27. Therefore, x has to be 3. Let's take a look at another one. 16 is equal to 2 to the x power. Well, I know 2 times 2, this would be 2 squared, that's 4. 2 times 2 times 2, well, that's 2 cubed. That equals 8. And if we multiply 8 by 2 again, that's what would equal 16. 2 to the fourth power is equal to 16. Therefore, x itself has to be 4. So good, I've got 2 solutions for these exponential functions. Let's try one more. 4 to the x power equals 15. Well, 4 to the first power is just 4. 4 to the second power would be 16. How would we get 15? I can't raise 4 to the second power. That would equal 16, and that's too much. I can't stay with 4 to the first power. That wouldn't be enough. 4 to the first power is only equal to 4. What would I have to do in order to get 4 to some power to be equal to 15? Well, I need a number between 1 and 2. But what is that number, and how do we find it? The number will be a decimal, and we can find that solution if we consider the techniques that we're now using in order to solve for x. Throughout these first few examples, we would undo operations from one side of the equation to the other. And the technique that we use to quote-unquote undo an operation is to use its inverse. For example, if I had x plus another number, the opposite or the inverse of addition is subtraction. So to move a number that's being added, I would then turn around and subtract it to move it away. To undo a multiplication, I would divide. To undo a power, something raised to the second power, I would take its square root. Something raised to the third power, I would take the third root, and so on. Each of these pairs of operations are inverses to one another. Now, last week we learned about exponential functions, and that's where the variable is left in the exponent. To undo an exponent, the inverse of an exponent is the logarithm. And that's what we're going to work on this week, using logarithms and evaluating logarithms. This information comes from page 353. And here's that definition blown up just a little bit. For the definition of a logarithm, we say that let a be a positive number where a is not equal to 1. The logarithmic function with a base of a is denoted by this symbol, log with a small subscript a. So we would say logarithm base a is defined by logarithm base a of x is equal to y. Equivalently, what that means is that a to the y power is equal to x. This definition of a logarithm is a strange one because we define a logarithm in terms of what it would look like rewritten as an exponent. So when we use the definition of a logarithm, and when we use logarithms here at the first part of this week, I want you to get used to writing a logarithm or understanding a logarithm in both its logarithmic form and its exponential form. So take a look real closely again here. Both exponential functions and logarithm functions have a base value. And what we're saying here is if I write this function logarithm base a of x, if I wanted to find the logarithm base a of x, and we know that that's to be equal to y, then this is exactly the same. It's equivalent to the equation that base a raised to the power y, and that would be equal to x. Now, I don't expect you to fully understand this expression right now. You'll see how it works in time with several practice problems, but we will see how these two correlate to one another and how we can use them to solve equations for x, an unknown variable, or y, an unknown variable. And this final comment in this blue box is a nice one too. We'll come back to this in our exponent rules a little bit later this week. The logarithm base a of x is the exponent to which the base a must be raised to give x. So in other words, the a base raised to the power of logarithm base a of x will be equal to x. And this is one of those definitions that we're going to come across a little bit later. You'll see its uses at another time. But for right now, this statement is giving us this rule, and we'll use it as we go forward from here. Let's try a couple practice problems as we get going here. Again, logarithm base a of x equals y. That's how we announce it here. Logarithm base a of x is y. Get used to using that terminology, please. If I would give you a word problem, or if I were to give you a verbal representation of this expression, I'd like for you to rewrite the equation. Logarithm base 2 of 16 is 4. Logarithm base 3 of 9 is 2. Logarithm base 1/2 of 1/16 is 4. So let's try this first one. Logarithm base 2 of 16 is 4. So I've rewritten this verbal description as an expression. Please try the second and the third example on your own. Pause the video and come back and check your work. And here we go with those two solutions. Logarithm base 3 of 9 is 2. Logarithm base 1/2 of 1/16 is 4. Immediately, I want you to consider what these logarithm expressions would look like rewritten as an exponent. So remember, the base of the logarithm becomes the base of our new exponent, or exponential function. The power then becomes the number that's on the opposite side of the equation, and the value that we're evaluating becomes the result of this exponential function. So to see the expression log base 2 of 16 equals 4, that means the exact same as this. 2 to the 4th power is equal to 16. And that's true. 2 times itself 4 times is 16. For this next example, logarithm base 3 of 9 equals 2. Well, this says let's write 3 raised to the 2nd power. That is equal to 9. And again, true. Last example, logarithm of 1/2 raised to the 4th power is equal to 16. So 1/2, oops, I think I said that wrong. Logarithm base 1/2 of 16 is 4. When written as a exponential statement, 1/2 raised to the 4th power is 16, and that would be true. A half, oops, not 16, but 1/16. A half times itself 4 times in a row is 1/16. So that looks like a good stopping point for this first video today. It's all about learning the logarithmic notation and how to rewrite an exponential function as a logarithm. In the next video, we will practice solving for variables. So we'll get used to finding variables in place of this result here or this result here. And we'll see how we can use this definition of a logarithm to our advantage.